This is a video lecture for Math 110 for Monday, April 27th. And the topic today is applications of the laws of sines and cosines. Actually, I'm going to do three parts to this video lecture. This is the first part. So over the last few days, we've been talking about the law of sines and cosines. And these are basically the laws we use to solve triangles that are non-right triangles. And just to remind you guys, the law of sines states sine of angle A over side A divided by sine of angle B over side B equals sine of angle C over side C. And we can also invert this, take the reciprocal of this, and that's also an alternate version of the law of sines. And the law of cosine states that A squared equals B squared plus C squared minus 2BC cosine angle A. Okay, and there are also two other versions of the law of cosines, which are the same law, just applied to different sides of the triangle. So you could also write B squared equals and so on, and C squared equals and so on. So these are the two laws we've talked about, and hopefully you guys are comfortable with these. We're going to consider three applications of the laws of sines and cosines today, three problems. And our first problem has to do with, and there are many problems and applications. These are just three I've chosen. The first problem has to do with a group of hikers who are approaching a mountain. And when they're a certain distance away, when they're 1,250 meters away from the mountain's base, what they do is they measure the angle of elevation of the mountain to be 35 degrees. And I'll talk about in a second what the angle of elevation is. And then they walk towards the mountain, and when they reach the base of the mountain, they measure the slope of the mountain to be 48 degrees. So before we even answer any questions as far as this problem goes, it's a good idea to draw a diagram of the situation. And so what I'm going to do is draw a very simple diagram like this. Here we have, let's say we have a flat area, and then we have our mountain rises up like this. And just for simplicity, and I apologize to any mountain climbers out there, hikers. I'm a hiker myself. This is going to be an oversimplification of a real-life mountain. We're going to assume this mountain has a conical shape to it, a perfectly conical shape. We'll assume the land is flat coming up to the mountain. And what this problem says is when the hikers are 1,250 meters away from the base, so let's draw a hiker over here, very small hiker, probably still too big. But anyway, our hiker is right here. When they're at this point, and actually I'm going to use a different colored marker for this. When they're at this point, what they do is they measure the angle of elevation to the top of the mountain. In other words, if I draw this line like this, they measure this angle. The mountain rises up 35 degrees above a level plane. Okay, so they measure this angle of elevation. And then what happens is they walk 1,250 meters. So this distance is 1,250 meters. They hike to the base of the mountain, okay? And let me draw this dashed line here as a continuance to the level ground. They hike to the base of the mountain, and then they measure the slope of the mountain, which is basically the steepness of the mountain, to be 48 degrees. So they measure this angle to be 48 degrees. Okay, so this is a diagram of our situation. I'm actually going to erase this over here a bit. So that's what we have here. We're going to ask ourselves some questions about this hiking group. And the first question is, so these hikers reach the base, and then they hike up this mountain. How far do they need to hike up the mountain? Okay. So after they reach the base, they're going to hike up this mountain. How far do they have to hike to reach the summit? Now, by the way, also for any hikers out there, this is a ridiculously steep slope, and no human will be able to climb this kind of slope. But just for the sake of this problem, let's assume we have a slope of 48 degrees. Okay, so the first thing to note here is we have a triangle. We have a triangle right here, and it's certainly a non-right triangle. And I'm going to label some different angles and sides of this triangle. I'm going to label this side D. Okay, and I chose D just for distance. And I know that's side D. And then I want to try to figure out, what D is. How far do they have to hike up the mountain? Now I only know one angle in this triangle so far, and I know one side. But I actually can figure out this side right here. This side right here, let me do this in blue. This side right here Okay, how do we find this side right here? Well, that side right there will be equal to, if you guys see that this side is what's called the supplement of this side. These two angles have to add to 180. So 180 minus this side, which is 48, that's going to equal 132 degrees, right? And so this side right here is 132 degrees because it's the supplement of this angle. So now look at what we have. We know this angle, this side, and this angle. So now we have an angle, side, angle triangle. Okay, this is classic law of sines. The first thing I can do is figure out what this angle is right here. What is that angle right there? To do that, I take 180. I know the angles of a triangle add up to 180. So 180 minus 132, okay, minus 35, right? And that gives me this angle. And if you guys calculate that, let's see, we have 48. This comes out to 13 degrees. Okay, so this angle right here is 13 degrees. All right, now I know all the angles of this triangle, and now I can solve for D by using the law of sines. So I'm going to use the law of sines, and that says, I'm going to use the inverted version of the law of sines. That says D divided by the sine of the angle that's opposite to D. Okay, I didn't actually label the angles on other sides with letters, but we can still use the law of sines. Side D divided by the angle the sine of the angle opposite to D. So sine of 35 degrees. Okay. This is equal to this side length, 1250, divided by the sine of the angle that's opposite to 1250, which is 13 degrees. So I get sine of 13 degrees here. Okay. And if I now solve this for D, if I solve this for D, I get D. I'll let you guys verify the algebra steps here. D equals 1250 times sine of 35 degrees. All of that divided by sine, of 13 degrees. And if we plug that in our calculator, we get 3187 meters. Okay. So this is now how far the hikers hike up this mountain. They'll have to hike 3187 meters to climb this mountain to get to the top. Okay, this is a really fun application of the law of sines to a mountain climbing problem. A second part of this problem has to do with the height of the mountain. You might actually be curious about what is the height of the mountain. Okay, any kind of mountain climber would want to know that. In other words, the vertical elevation rise of this mountain above the land here. Okay, what is the height of this mountain? How do we figure this out? To do this part, we can actually start at the summit here, and I'm going to drop down. I'm going to drop down a perpendicular line here, okay? And I'm going to call that perpendicular line H, okay? By the way, now I know this distance right here is 3187 meters, right? So now I have H here. Okay, here I have a right triangle, right? If I zoom in, I've got this triangle here, but by dropping down this perpendicular, I've created a right triangle right here. So now I have a right triangle here, and I can figure out the height, and hopefully you guys see how to do that. Let me zoom in, let me redraw this right triangle. I now have a right triangle that looks like this, where this is H, this is 3187, and we know this angle is 48 degrees. Okay, we want to figure out H, the height of the mountain. Okay, how do we do this? Well, we know how to tackle a right triangle. Basically write sine of 48 degrees equals the opposite side, which is H, divided by the hypotenuse, which is 3187. And this leads us to, if we solve for H equals 3187 times sine of 48 degrees. And if we plug this in our calculator, we get 2368 meters. So the height of this mountain is 2,368 meters. Again, so this is a fun application of the law of sines to a real life problem. In parts 2 and 3, I'll consider some other example problems with some applications.